much we're in the prototyping phase for some LC300 recovery points. We do a lot of our designing on Fusion. That's where we can kind of model, simulate, and post all the programs for us to actually machine it on the machines. So I've just gone through and I've modeled everything up, and the cool thing is, like, we can kind of simulate everything on the computer before we run it in the machine, just to make sure it's going to work. So we can kind of see exactly what the machine's going to do, which is very, very handy. So we're drilling all our holes, facing all the material down. This one was quite tricky because it's got so many different kind of faces and angles and everything. Took probably, I'd say, a good hour and a half to get it all kind of programmed and figured out. It all kind of depends on the complexity of the part, but this one is a little bit more complex.
Does it depend a lot based on the machine you're using as well, whether it's like a 3, 4, 5 axis?
Yes, definitely machine capability helps a lot. So, like, for example, this could probably be a little bit better if we had like a 4th axis type setup for it, then we could rotate and have faster tool paths. But for the moment, this works perfectly fine and it is still pretty efficient. So for the production batch, obviously we want to make it kind of as cost effective as we can in case we've got to make changes to it. So for example, I've just got one little fixture plate that will hold everything. But when it comes to a production batch, we'll try and have multiple set up in one machine, so then we can kind of run heaps of parts at one time. That just makes a lot more efficient, and the cost per piece gets a lot cheaper as well. And I think we are ready to burst. Computer time. Oh no, CNC time. So with this machine here, it's pretty intuitive in the way that it can kind of show us the program as well, so we can make sure what's being simulated on the computer is the same of what's going to be on the machine. So if I just open up my program here, so we can kind of see everything on here as well, and just kind of double confirm that we're not going to have any issues while running the part. Generally, you don't have any issues when you simulate it on the computer. 99% of the time it's going to be correct, but sometimes you can have small anomalies that we don't really encounter. But it's just a good peace of mind, just making sure the computer draws it the same as the computer. We've already done one side here, so this is kind of what we've done. And it starts off as some raw material just like this. And I've tried to design this to be just like a one operation type part. So instead of like taking it out, clamping it in different orientations, it's just one setup and away we go. So initially, if you were to look at this part, a lot of people would probably try and hold it like this and just drill these holes and machine that. And then they probably want to clamp it something like this to machine that chamfer. I don't like holding stuff in multiple handling and all that type of stuff, so I try and make it as simple as possible just by having one setup, and you don't have to kind of add all the extra motion and changing things. So yeah, so this is the fixture I had to design as well, hold that down and everything. Just got temporary stops just so I can move it all later. So just make sure it's all loaded in properly, tighten it down.
And how do you get registration correct on the machine? So how do you know when you're loading this part that it's exactly where the machine needs it?
So when we initially set up the job, you set up all it's called the datum point, so all its coordinates. So my datum point, for example, is this edge here. And when you set that, it pretty much remembers it for the rest of the jobs. So we can start running this program and start cycle. Then we'll start running the program that I had on the computer over there, just so I can make sure everything's going to be in the right position. And I'm pretty happy with that. I actually get simulations on how long it expects it to take, and this part here roughly takes around 12 minutes. And I'm hoping, like, when we start doing more of a production batch, we can hopefully get that under 10 minutes. Right. We put our bolts in. We're using countersunk bolts, so it locates on the holes as well, so it's going to be perfectly located. Now we can remove these ones because we have to machine the outside of this part. So now we're only held down by these two bolts. And now we can literally machine all of this part without having any fixtures or clamps in the way. Some no coolant action. anything with like 3D milling is pretty satisfying and cool to watch, because like you just see the machine doing all these funky movements. It's just, I don't know, just that's what everyone dreams about when you're doing milling. Just want to make sure nothing crashes, all my heights are set right. So pretty much everything moves simultaneously to create a nice smooth chamfer. Sometimes the press profiles might not be super accurate, so that's why it's doing a little bit of air cutting at the moment, just to give it that bit of leeway. So now we're starting to take some material off. There we go. And that's how we get the whole contour. It's just so satisfying to watch. Instead of kind of having it like this, machining around and putting the chamfer on, you can do it all in one because of all that 3D milling. The finishing pass now. It's very important to make sure your stick outs are all the right height, because I could have easily just put that in close and just crashed straight into that part there. So you have to be very vigilant when you're doing all this type of stuff, because it's very easy to have big boo-boos. And that is pretty much part done. Very clean.
Ta-da.
But it's full of burrs at the moment, so we've got to safely knock them off. Just with the little pencil deburring tool. When it comes to the production batch, we'll try and have a lot of this deburring done in the machine, but just for prototyping sakes and to save a little bit of time, I just thought it would just be easy to knock it off by hand. But yeah, obviously we want to try and make the machine do as much as the work for us to make our life easier. We have a done part. This is what keeps me up at night. No, that's a bad thing. That's a bad saying. This is what I look forward to every day. Getting to see this shiny stuff. Yeah, makes me happy.
You're so cute. How are you so cute?
We've had this 250 for about 7 months, and initially when we had a good look at it, we were going to build it up as a family touring vehicle that had a little bit more space. We could tow our camper behind it, and we wanted to sort of facilitate that sort of use case. Now what we've done is we've added all the rear storage in the back, we've got the roof rack, and we're working on a bunch of other bits and pieces. Some things we've released, some we're still working on, for example underbody protection, compressor mounts, recovery points, and some comms, aerial brackets and so forth. Now we've taken on a few trips, and that's allowed us to understand what works and what doesn't work, the strengths and weaknesses of the vehicle as well. So on our recent trip to Gari, one of the things when I was cleaning it was the fact that even though we've got the rubber mats in there, they didn't really stop the sand from getting in the carpet. So we're going to get some new floor mats that should hold and capture that sand a lot better. We were bottoming out a fair bit. Even though the suspension's quite nice, it just didn't give us that clearance. So we've got a lift coming as well. And we had a prototype underbody protection installed to the vehicle on Gari, and there's a few things we want to revise in terms of the strength of the bash plates and the sand and the way that it actually fits. Now, we also want to actually have a look at whether or not we need extra bracing at the front of this vehicle, being that this vehicle is actually quite low at the front, even though the overhang's quite short. So we're going to do a little bit of analysis on the chassis material as well. this front cross member, this radiator support, is actually quite weak, and if you have a look at it, it's only just sort of like a C-section there, so it's not sort of connected to the rigid chassis here. Now we've designed some supports here. These are just 3D printed prototypes to check fitment, but what we want to understand is how much load can this front radiator support actually hold, and we're doing a little bit of simulation and FEA to do that, but we need to understand what grade of material this is. So we're going to use our hardness tester and compare the Toyota chassis material with some material that we know the strength of. You can see it in there, there's a little ball on a spring, and when you cock this and let it go, it sends a ball down there and it bounces it off the material. And depending on how hard it is, you'll see how far it bounces back. So what we have here is some 1020 material, mild steel, fairly common grade of steel, and here is some high tensile 4140. And essentially what we do is we cock it, the ball goes up to the top. You hear that? You hear the ball bouncing? Then you can compare it to this 4140. Ooh, you see, it definitely has a higher pitch, much harder material. So that's how we compare. And it gives us a value on this readout. But what we're going to do is we're going to compare the softer material, the 250 grade material, to the Toyota chassis material, which we reckon's somewhere in between the mild steel and a high tensile steel, and then we can have a good guess, or we can actually determine how strong the chassis material is. So this spits out a hardness number, but we're more concerned about just comparing it to different materials. So the number doesn't really need to mean too much for us, but it just gives us a way to compare the different materials. Otherwise, we'd have to get this calibrated, and this is valid as well, what we're doing. So have you got?
Trust me.
Trust me. I'm an engineer. Now the important thing with this tester is you actually have to have enough mass behind it to have enough inertia for that ball to bounce back. On the chassis, it's generally sort of thin material. We have to actually put enough material behind it, and what we've done with the panhard, we've been able to clamp a block of steel on there. So we'll go and do the testing and we'll get some numbers. We're at the back here on the 250 because we need to do some analysis on this mount for our development of the panhard relocator for the 250. So we need to understand the material here, and we're making the assumption that this material, this bracket here, is the same material that's going to be on that cross member on the radiator there. Now the reason why we're testing here is because we can clamp a nice solid block of steel on the back there to take up any gaps and make sure there's enough mass behind it so we can do the test properly. So what we're doing, we've got that block bolted there, and we're just going to test as close as we can to that bolt. And that gives us a reading. Now we're also making some assumptions around the fact that the paint on that surface will actually reduce the reading that we get, but that's a conservative approach instead of me trying to grind all the paint off. So cool. So we'll go and put that into a spreadsheet and work out what we think that material is.
How do you isolate the performance of the steel that you're testing against versus the steel of the panhard, out of curiosity?
Well,
obviously I'm not an engineer.
The indentation is actually on the material here,
Yeah.
and what's behind it doesn't affect that reading.
Yeah, so it's just the surface.
Yeah, so it's taking the hardness of this material here and having that block of steel bolted to the back so it's attached to the rest of the chassis gives us that sort of inertia and the backing so that we actually get the true hardness reading of that material on the front. Yeah. Otherwise, if I didn't have that there, I wouldn't be able to get the right reading, and we've tried it all over the vehicle. This is hollow, and if you actually test it there, it'll give you a very low reading.
So why is it being hollow such an issue? Because the material moves?
Yeah, because it's such a sensitive instrument that having just a little bit of deflection or a little bit of, how would you call it, sort of like a membrane effect affects the readings. And we've noticed that on the 150. So we've done this test on the 150 as well and got similar results. We're finding that this material is a little bit stronger, and that sort of correlates to the fact that Toyota have actually said on the 300 series and the 250 series chassis, they're using a slightly higher grade of material. And it sort of shows because some of these brackets and so forth are actually thinner than what you see on the older vehicles. Just from these numbers here, I can tell it's definitely a higher grade than the 1020 or 250 grade mild steel that you commonly get. and it's not as strong as the high tensile 4140, but it's somewhere between, and it's actually a substantial difference, and it will actually make a difference to our analysis and our FEA. So it's really good that we've actually got this result.
So this is just a stress analysis. This is based on just a load in the middle. And I think the big issue is Toyota didn't enclose these sections here, so it's just like a channel, isn't it?
Yeah.
So we put those results in there, and we've also done one with some extra bracing in there. So
Yeah. So we've added some bracing that connects from the chassis here
across to there.
Across to there is there. You can still see there's still a very high stress there, but that stress is much smaller, and the deformation there, even though we're seeing this red's just the highest deformation on the simulation, that doesn't actually mean good or bad, but we're only seeing 2 mils of deformation here. Previously on this one here, according to our simulations, we're seeing 5 mils of deformation.
So, yeah, less than half. These braces we've tried to design be nice and simple to attach to the chassis and also attach to the cross member. So I think that's going to make a big difference. It's going to give us a much more reliable, stronger situation if you were to hit the front edge of that bash plate, which is more of an issue on the 250 because it sits down a bit lower. So yeah.
So this is our new toy. It's a laser welder. We've had it for a while, but we've just taken our time to set it up properly from a safety point of view. So it's a 1.5 kilowatt laser welder. So a laser beam comes out of this gun and it melts the steel and feeds the wire in, and it's very quick, very neat, very tidy, really quick to learn as well, but there's other little things that make it very different from traditional welding processes. So we're keen to learn and keen to apply this to our products to make them a bit more efficient and pretty. There's version 2 of 250 underbody protection. I might need to practice first, before I weld the actual thing. We've made a cradle now instead of clamping on around the cross member. These are some prototype locators, Front brace,
so
front brace.
that fella hangs in there and it
positions
sort
it.
of lines that up,
Cool.
So we'll probably melt the printed ones, but we'll just check how they go.
If I tack them up the top, it'll be fine. Yep.
Under there, and then I got it from the bottom.
That locates it like that. So we have another one on the other side.
Yeah. So
Okay.
that way we don't have to have those notches where you
Yeah.
see the weld bleed through on the other side.
That's it. Okay. Some. Roll on. Good.
ScoMo meme. You know, when he lifts up the welding helmet.
You said here? Yeah, you gotta do it.
That's why we double shielded, aren't we? So this is going to be a good one. And lift out. Yeah. How's that one?
Hey,
How's that one? That one good?
that one's good. We might get you P plates today.
I've got the hang of it now. This fits up really nice. This weld, this weld, this weld, this weld, but I'll tame it on this side. Very different gun as well to hold compared to the mid gun.
Is it as ergonomic?
Nope, it's terrible. I hope I can get better guns, like my fingers in the way and
Where do you pull? What's the trigger?
little something right there. Little trigger in there. And the wire feed on the mid gun usually goes straight through the middle, but this goes on the bottom, so that's why it's sort of in the way for me at the moment. I like that one. I'm going to do this weld here. Well, we'll see. It's a huge gap, so I don't know if I'll be able to do it nicely. Well,
How much of a seam can this gun put down?
Well, you can actually get laser welders with 2 or 3 filler wires, because the laser can melt so much steel so quickly, you can feed more wire, but this is just got the single wire. very pretty. So use these guides to tuck it in place. Okay. Yeah, once you get used to it, it's pretty good. So this is fully welded, this front guard. And even though these welds might look small, they're super strong because the laser gets such good penetration. Let's make sure I haven't popped through. You see how much heat comes through that laser? But because the welds are so quick, you actually don't get the distortion that you get with MIG welding. So it's definitely a much nicer product. It's still super strong. You can see those welds popping through in really good penetration. With the X700 material as well. Yeah. That's going on my 250.
Whoa.
Oh, the sand. What's he up to?
I'm up to needing a hammer.
I reckon it's at least an inch longer cable.
Last one.